So the other two colligative properties that we're going to look at are the freezing point of a pure solvent versus a mixture, and the boiling point, pure solvent versus a mixture. Freezing point depression, like we said, a solution freezes at a lower temp than the pure solvent would. Water freezes at 0 degrees C. Salt water is going to freeze at a temperature lower than 0 degrees C. Any solution is going to freeze at a lower temperature than just the solvent by itself. Boiling point elevation. A solution does what? Boils at higher. So again, salt water. Water boils at what? 100. I have salt water. What temperature is it going to boil at? Higher. That's why you're not supposed to add salt to your pasta water until the water itself is already boiling. Because if you add the salt at the beginning, that's fine. You've just made salt water. It just takes longer to reach its new boiling point, right? Yeah. Yeah. Once the water's already boiling, add the salt. Yeah, then it still technically has to then climb a little bit more to get to its new boiling point, but it doesn't take as long as starting from the bottom, and now we're here, right? Okay. Next time, now you remember Ms. Poe said add it at the end. Okay, so when we talk about the elevation or the depression, we are talking about solving for or measuring a delta T, a change. Delta T of the freezing point is what? Final minus, what did I have on here? Yeah, it just says TF. Okay. Final minus initial. Always delta is final minus initial. Solvent, no, sorry. Final would be what it is now when it's a solution. Okay. It's the new lower point. Initial is what it is when it's just the solvent. Right? Okay. Boiling point. How much is it changing? Delta T of the boiling point, right? Same idea. Final minus initial. Okay. Up here on the screen, I wrote do the solvent minus the solution. I don't want us to get all caught up in what goes where, because here's why. Let's keep it that way. Let's keep it solution and solvent. Here's what I want you to think about when you're calculating these deltas. Let's just take the absolute value. What is the amount that it elevates? What is the amount that it depresses? Just give me the absolute. Just calculate the absolute difference. What's the absolute difference? Okay. So again, I'm not worried. What I'm saying is I don't really want you guys to be worried about, well, which one am I calling final and which one am I calling initial? Okay. That's what I've decided. Let's not worry about that. Just take the difference and use the absolute value. Right? I don't care. Just take the difference between solvent and solution. Just take the difference. And you're taking the absolute value, right? Absolute value. Because the freezing point is going to do what by that change? Lower, decrease. How do you get the new freezing point of the solution? With that information, you're taking the freezing point of the pure solvent, and you are subtracting that change you just calculated, right? Depression, lowers, subtract, yes? Subtract. And that gives you the new freezing point, right? That gives you the lowered freezing point. Over here, what are we going to do with this change of the boiling point that we calculate? We're going to calculate a positive value because we're just going to calculate the absolute value, right? We're going to calculate an absolute value. What are we going to do? What does that mean our new boiling point of the solution is? Well, I got to take the boiling point of just the solvent. And then what am I doing with this change I calculated? This is an elevation I am adding. See? Okay, what if I don't have a final and an initial temperature? What if I don't have that information in the lab? Is there a way I can still calculate delta T? Absolutely. These are the equations I gave you. You see the equations for boiling point elevation and freezing point depression. See those? Okay.
So you'll want us to find it like this, or?
Well, I mean, it depends on what information you have. If you were told, here's the temperature it normally freezes at, and then here's the temperature the solution freezes at, what's the easiest way to find delta T? If you're only told information that is in this equation, then this is the easiest way to find delta T. So what information is in the equation? Let's look. For the freezing point, delta T freezing is equal to what? What is that I? Look on your useful equation sheet. What do I say that little letter I means? This is not like the imaginary number in math, okay? It's not that. Yes, okay, so it's something known as the Van't Hoff factor. But it essentially means how many separate particles does your solute dissociate into? You remember the word dissociate? Dissolve, ionize. You remember those words that we used last week? So, if I need to find my new freezing point, first thing I'm finding is, well, what is the amount of change it undergoes? Okay. And that means taking how many particles my solute splits into. Do covalent particles split? Do non-electrolyte particles split? No. That's why I taught you guys that first last week. Any kind of covalent compound, when it dissolves, it's just dissolved. It is not ions, right? How are you recognizing if it's a covalent compound? You should recognize if it's just, carbons and hydrogens, and if it's non-metals, that's covalent, right? You might also see a solvent, a solute described in a problem as a non-electrolyte. If it's a non-electrolyte, when it dissolves in water, how many particles are there? One. Did y'all hear that? If it's a non-electrolyte, when this dissolves in water, how many particles does this make in water? One at a time. One at a time. Non-electrolytes, the I value is 1. Non-electrolytes, the I value is 1. Electrolytes, well, how many ions does it split into? Yeah, it depends. Well, we're going to look at the formula, right? And we're going to count how many different ions it splits into. But what comes after I? What is that lowercase m? The molality of the solution. And then there is this K value. So this is now a capital K. And if we put an F here, that is referring to a constant for that substance. It's called the freezing point depression constant. It has to be given to you. Okay. Boiling point, same formula. Find the change. Number of particles times the molality of the solution times a constant value for that solvent, Kb, that has to be given to you. Let's try one. Let's look at 19 on our in-class examples. Freezing point depression is what our lab is today. Our lab experiment is actually also tomorrow when we make the ice cream. We make the ice cream ourselves tomorrow. We're going to also still be investigating freezing point depression. So I really want to focus here in class. Let's do these boiling point examples. And then in the lab, we'll do examples about freezing point depression. But again, it's the same problem approach. Okay. It's like almost identical formulas, it's the same approach. Okay. What's the main thing you got to remember? If it's freezing point depression, you got to subtract that change. If it's boiling point, you got to add that change. Shut up, Veronica. Now, when you read 19, how do you know that this is a collutive property problem? Okay. What is the boiling point of a molal solution? Guys, this is the only time we're using molality. If it's molality, it's one of these. Of a non-volatile solute. Okay, so I used a word there, right? I said before the break, non-volatile can mean what? It doesn't have a vapor pressure. Okay. I really should have added the word here, and I'm sorry I didn't, so you guys add it. Non-electrolyte. I'm telling you that the solute, whatever it is, A, doesn't have its own vapor pressure, non-volatile. And now I'm telling you to add the word it's non-electrolyte, which means how many particles does it make? Just one particle when it dissolves. Perfect. Okay. We're dissolving in this compound called benzene. Benzene is very, 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 very dangerous for you, and we use it all the time in organic chemistry. If you want to know what benzene looks like, it looks like this. There you go. You're like, that's not a compound. This way. It is. It's a way we draw organic compounds. You'll learn. I'll teach you. There's a carbon. 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 There's a double bond. There's a double bond. There's a double bond. There's a hydrogen. There's a hydrogen. So actually, this circle in the middle is kind of a even more short. There it is. That's benzene. Do you need to know that? Not right now. Maybe at the end of the semester. Okay. What's the boiling point? So what does that mean? I first have to find how much the boiling point changes. How much does this boiling point increase? What's my solvent? It's this compound benzene. What's the freezing point of just pure benzene? I should tell you here in the problem. Excuse me, I'm saying freezing point. I meant boiling point. I don't expect you guys to know anything's boiling point or freezing point except water. I expect you to know water. Anything else I'll tell you. 80.1. What else am I giving to you? I told you that constant value that you need, Kb. 2.53 degrees Celsius per molal unit. And because it says it's non-volatile, and I told you now to also add the word Really, this is the more important word here. It's a non-electrolyte. That means the number of particles is just 1. You take 1 mole of this solute, it makes 1 mole of particles. It doesn't split any more than that, just 1. So, Caitlin, can I calculate T final minus T initial for this problem? I don't have 2 temperatures. I just have the 1. So let me use this formula to find the change. IMKB. Now, how do we calculate molality? Moles of solute divided by, my bad, it did give it to us. What? Okay, but what if it didn't give it to you? What would you do? Figure out how many moles. Divide by how many, what? Kilograms. Mm-hmm. For the percentage, excuse me, for the percentages, yes. A percentage concentration is defined as being out of 100 of that unit, whatever the unit was. Okay. All right, so this. So what does it say the molality was? Excuse me. 0.33. So you guys know that that means there's what? 0.33 moles per every how many what? 1 kilogram of solvent. You always need to remember these concentrations are 2 units together, right? We often just write the little 1-letter symbol, like we write just 0.33 M, but you got to remember that M truly means these 2 units are both represented, right? Okay. Okay. Delta T. 1 particle times 0.33 molal, the concentration, times 2.53 degrees C per molal unit. And that gives us a temperature change of what? So that the molal units cancel. Okay, so my answer is a temperature change in degrees C, 0.8349, right? Degrees C. How many sig figs should this number have? 2 sig figs. What about the what? Oh, that's a exact number. The number of particles, this is a good point. This is a good point. The number of particles that are formed, if we're just estimating that number by saying covalent just makes 1 particle, that's a counted number. I counted how many particles it was going to make. Counted numbers, we don't count towards sig figs. You may come across some problems in active chem where it gives you a calculated I value. That can be done if you had a calculated value given in the problem. Should you a calculated value? Should you think how many sig figs it has? Absolutely yes. If it's just you estimating the number of particles, then no, don't count. Okay. So if we're going to round for sig figs, 2 sig figs. So 0.83, because that 4 doesn't round that 3 up. But again, is that the new boiling point? That's just how much the boiling point changes. So the new boiling point is pure solvent plus the amount it elevates. Now, where does this answer stop? The tenths place. Because as I'm adding these two numbers together, the last sig fig for this measurement was in the tenths place. This goes to the hundredths place, but I got to stop at the first one I come to going left to right. I got to stop at the tenths place. That's where I have to stop. That's where I got to cut it off. So what's the new boiling point? 80.9. If it is an electrolyte, it will either give you an I value or look at, let me see if I can give you, because we're out of time. Let me see if I can give you an example. Look at number, okay, real quick, look at number 22. I'm not going to work this one right now, okay? But look at 22 where it says, what are you dissolving? Can you tell me what the identity of the solute is in number 22? Calcium chloride. And I very intentionally did this. I had you guys dissolve calcium chloride in the test tube last week, right? And I had you write a dissociation equation. And can you guys look back at your notes at number 1 on your in-class examples and tell me how many particles, how many separate particles total does that calcium chloride dissociate into? 3 ions, right? A calcium ion and 2 chloride ions, right? Okay. So for example, when you would be working, practicing number 22, your I value would be 3. Very good. Very good. Very quickly, let's just look at this equation, okay? And then we're going to go down, to the lab. And like I said, y'all are doing a freezing point depression today. We'll practice some more of this math. Osmosis or osmotic pressure. Do you guys know what osmosis is? Some of you, I'm sure, do. I always have to remind myself because, again, I'm not a biology person. But what is osmosis? Solvent molecules moving back and forth. Across a what? Semi-permeable membrane, like a cell wall. Why do solvent molecules move? They are trying to even out concentrations. Absolutely. So something where there's a whole lot of solvent, a side where there's a whole lot of solvent, like this side, has very little what? If it's all solvent or almost all solvent, then there's very little to zero what? Solute, right? No solute. The other side in osmosis has solute in it. That's these blue circles, yeah? Which way are these yellow solvent molecules going to flow? To the side where there's a lot of solute, right? Because it's trying to do what? Even it out. It's trying to dilute that other side. Osmotic pressure is when that movement happens, okay? When that movement happens between the sides, there is a pressure difference now from one side to the other. That's based on how much solvent moves, okay? There's a pressure difference. That's what's known as osmotic pressure. I don't need you guys to define what osmosis is or what osmotic pressure is. I don't need that. What I want is for you to understand that this is what is known as a what kind of property? Colligative. Why? Because it depends on how much solute is on one of the sides. Absolutely. The more solute you have on one side, what does that mean about the pressure? Do you suspect? The osmotic pressure. The more solute you have, more and more and more solvent is moving to that other side, right? you end up with a very large difference in volume between the two sides. A very large volume difference means a large osmotic pressure. Yeah. Okay. So I think I may have at the beginning of class written osmotic pressure lowers. Scratch that. It increases. Well, I mean, it depends on what you're doing, but let's just say the more solute you have, the more the osmotic pressure increases. Okay. Higher concentrations means higher osmotic pressure. There we go. That's really what I was trying to say. Okay. Is there an equation to calculate this osmotic pressure? Yes, of course there is. And this is it right here. Should this just really be a kind of a plug and chug? Yes, it should. We've already talked about what is I. What is I? It's the number of particles, right? How do you know how many particles? If it's a covalent compound, if it's a non-electrolyte, it's how many particles? 1. If it's an ionic compound, count how many ions there are. In osmotic pressure calculations, we don't use molality. We use our good old friend, molarity. Moles of solute per liter of solution. Absolutely. Temperature. Kelvin. R. Now this is the R value that we used in Gen Chem 1. This value. So don't forget that when you're doing calculations in chapter 10 with enthalpies of vaporization, you got to use that R value. If you're doing osmotic pressure, you got to use this R value, right? That is on this paper. I think. Yeah, it is. Okay. So perhaps down in the lab, we may try to work one of these osmotic pressure problems as well. That would be like number 23 and 24. No, 23, just 23? 23, 25, I don't know. Anyways, we'll look at some. And if we don't work them down in the lab, I might work one very first class tomorrow. But guys, I think I've decided that we're not gonna talk about colloids. Yeah, 11.5. Let me see what I think about first thing tomorrow morning, okay? So, what this means is that even if I do cover colloids, I would cover just some basic definitions, which I might do that. What does it mean to be a colloid as opposed to a solution? I might just give a basic definition. So what this means is that you are more than, of course, able to finish the first set that was due tonight. The only thing you needed to finish that set was me teaching you about gas solubility at the very beginning of class. That was like the last 3 questions or something on that set. So now you're going to have a second set over these colligative properties. What do we do Wednesday night? Because first test is Thursday morning. Right? Okay. So there will be a chapter 11 quiz, just like there was a chapter 10 quiz. That'll be due Thursday morning. I got to put it together. I haven't done that yet. I think I've decided that I am going to, for this first test, let's try this. I'm going to let y'all make note cards. I know. Rather than me just giving you a list of equations, I'll let you make note card. We'll do that. This is a 4-inch by 6-inch note card. You may handwrite whatever you want on this front and back. No. 4 by 6. Whatever you want, front and back. I don't care. Okay, but that means I'm not giving you this sheet, though, right? It's on you now to write all the information you need. Okay. I always give you guys for a test, of course, a periodic table. We don't need conversion factor. Well, I don't really think we need conversion factors for this. 1,000 joules and 1 kilojoule. I don't know. So, okay. So, all right. So if you guys will, head down to the lab. If you would very first thing, and then you can break a little bit longer. The lab sheet for today is down there on the podium at the front. Get a hot plate from the cabinet that's open and down there. Get a hot plate for your group. Get a 400 ml beaker. 400 ml beaker. Fill it about 300 mils of tap water. Not the squeezy water, just tap water. Put it on the hot plate and crank the heat up. We need to get that water heating, okay? Just crank it. And then we'll adjust it. We just got to get it hot. Pretty much boiling. Close to boiling. Then take a break, do whatever. Let's just get the water on the hot plate, and then we can talk about the lab itself more after y'all have a minute, okay?